We are now moving into the statistical mechanics part of the course, and we will make a connection between what we've learned in the first 18 lectures and how we understand things from a probabilistic standpoint. So before we get started, we are going to go back to a topic that we have discussed already in the past, which is the equipartition of energy. Well, we barely discussed it, but it turns out that we have seen it a few times, even though we don't call it that way. And I will make sure to make the connections with what we've seen before during this lecture. So we are going to look in a regime at high temperature behavior. You will see, and this is where we end this lecture, we will see that at a very low temperature, quantum mechanical effects start to come into the games. Therefore, the equipartition of energy is no longer valid. But we will see that. We also discussed that it's possible that in some cases the high temperature regime also is inadequate. But we will see that in usual temperature range, what we do here with the equipartition of energy is a very good approach to understanding the thermal properties of a material. So let's go right into it and talk about the equipartition theorem. And it turns out that this theorem really applies to any energy term that's quadratic in some variable. So that's the idea. So of course, that's the reason why this is so important is that so many such terms in quantum mechanics and in classical mechanics that are quadratic in a variable. While the most obvious one, of course, is the kinetic energy of a free particle, which is simply mv squared over 2. But also, many potential terms can be written that way. So, for example, the potential energy of a spring, of a mass that's attached to a spring, is 1/2 kx squared around its stable position. So that's what we call the harmonic approximation, and we will discuss this in much more details by the end of this screencast. This is the potential energy, and in fact, you can also write the total energy of this system as the sum of two quadratic terms. So this is very interesting because it turns out there is a important theorem, which we call the equipartition theorem, that will make our life much easier to deal with this kind of terms. So it looks all mysterious for now, but you will see that everything will work out and we will understand what's happening and make a lot of inference on what can be observed experimentally. So the question is that imagine that the system can exchange energy with its surroundings, for example, can absorb heat or can exchange heat with a reservoir at a given temperature T. So what kind of energy are we talking about? This is really the question we are trying to answer. Just to remind you, we have this energy here. And the question you can ask is that when thermal energy is stored, how can it be stored? Well, there are not many processes that we can consider. For example, it can be stored in the first term, which would be the movement of the mass, or it could be in the second term, which is the vibration of the spring. There is no other physical phenomena that can account for storing thermal energy. So this is really where the equipartition theorem comes into the game. They actually provide you a measure of how the thermal energy is stored in the system. In fact, it provides you how much of that thermal energy on average is stored in each of those phenomena, one being, for example, here the kinetic energy and the other one being the energy of the spring. Very good. So we can do this, and in fact, when we do that, it turns out that at finite temperature, we have a number of vibrations in the system. So here it's a solid, and then the artist here from this website tried to show the vibration of and the jiggling about of the atoms around the equilibrium position. So this is something that happens at temperature that's not equal to 0. and we can wonder what's happening and how can we explain the vibration, how can we explain the amount of energy that comes from the thermal energy. And this is really what this will be all about. So the first question you can ask yourself is, why is the quadratic term for energy so important in physics? Well, this is something that I'd like to remind you here. And again, one of the best friend of the physicist is the Taylor series that's provided here up to second order. And the question we want to see is that we know from physics that for reasonable energies, the system will be close to the minimum of energy. So that means that if we can model the potential energy around the minimum of energy, we should be able to really describe a number of phenomena that can be seen in a very broad range of phenomena that can be seen in practice. So that means that I can write this Taylor series up to second order. And in fact, the first order term, so this term right here, goes to zero. Why? Because it's a minimum. So we are talking about around this point x naught. This is, of course, a minimum, so the first derivative is zero. And we have a second term here, which is a quadratic term with the second derivative. And this second derivative, if you remember from simple calculus, is nothing else than the curvature here. So in other words, saying that we can write this as a quadratic term plus a constant, which is just a shift, is simply saying that I can approximate this curve with a parabola. And the parabola, of course, is pointing upward, so this term here is positive. And the reason why it's pointing upward, of course, is because it's a minimum, otherwise it would be going downward. So this is called the harmonic approximation because the system behave harmonically within the parabola. And it turns out that this kind of approximation can be done in many cases, can be done very often when the minimum is deep enough, and we have a very good approximation for the quadratic term. It is not always the case. We can have we can find cases where the harmonic approximation is not correct. You need to go beyond further order, and actually I will say a few words about that by the end of this lecture. Very nice. So let's go back to where we are going. We are saying that the terms that we are considering here are all quadratic terms. So here it's a good explanation. Of course, the kinetic energy is usually a quadratic term. We've seen that with mv squared over 2, but we will see that with the kinetic energy of rotation as well. So let's try to consider a general term where the energy is equal to alpha x squared. Alpha is some constant, depending on what we are looking at. And x is actually a general variable. It doesn't have to be position. It can be velocity. It can be any variable of the system. So the energy depends on some variable x in a parabolic fashion, as shown on the right-hand side of this slide. So now the question is, we would like to know how much energy there is in that, what's the average energy there is in a system like this when it is at temperature T. And so this is where we go back to one of the first lecture we looked at, where we discussed the Boltzmann factor. Remember, the Boltzmann factor provided you the relative probability of finding a system in a certain energy. So if we plug in the energy alpha x squared in the exponent here, and the beta here, of course, as you remember, is 1 over kBt, as we have discussed a number of times in this course. What we need to do is if we want to calculate the average energy, we simply look at the probability of finding a certain position x, so that means a certain energy alpha x squared, and we can calculate the mean energy. And the mean energy is going to be nice because, again, since the energy goes as a quadratic term, we end up with Gaussian. And as you know by now, the Gaussians are nice because we can do most of them involved, when they are involved in integral, they can be solved analytically. And in fact, when you do this, you find out that the average energy of a system that's described by alpha x squared as the energy at temperature T, actually that average energy is 1/2 kBt. And this is the equipartition theorem. So what's the big deal about this? Well, there is the big deal about this is that the expectation of the energy does not depend on alpha. So I mean, I just like to repeat this. So it's so important. The expectation value of the energy does not depend on the scaling factor for the energy, so long as the energy differ quadratically with some variable. So it could be mv squared over 2, can be kx squared over 2, can be anything, and we see other examples. All of those energy terms will lead to an expectation value of the energy of 1/2 kBt without any dependence on alpha. Further, because it does not depend on alpha, the system, the average energy does not depend on the mass, does not depend on the size, does not depend on anything like this. Just depends on a fundamental constant Kb and the temperature which is imposed by an external bath. So this is the important result here about the that we have about the equipartition energy, and then we'll get a better idea why we call it equipartition in just a second. But you can already see here the equipartition. Equi means equal, means that expectation value of the energy is equal for all the terms alpha x squared, basically. Now you may wonder, what kind of sorcery is this that the expectation energy does not depend on alpha? Well, the mathematical reason is on this slide, and it comes from the fact that we are involving Gaussian. And the reason why we have Gaussian is because we replace the energy on the Boltzmann factor by alpha x squared. You can also look at that graphically for those who like to have a more visual aid to understand what's happening. So here I've plotted three different value of alpha x squared, a function of x, for three different value of alphas. I just multiply by 1.5 and again 1.5 for the three curves here. And I pick the temperature such that kBt is equal to 1. Now, of course, I can calculate the Boltzmann factor. In fact, I'm going to divide here by this term so that we have a normalized integral. The reason why you need to normalize, of course, is because the normalization does depend on alpha. Anyways, the point remains that the Gaussian the larger the alpha, the sharper the Gaussian distribution will be. So already you have an idea that alpha x squared is broader and broader as alpha increases, while the Gaussian is sharper. And in fact, when you calculate the product, and remember, this is the term that we need to integrate to get the average energy, you are multiplying something that gets wider and wider by something that gets sharper and sharper, and you find those three curves right there. And so what happens is that the surface under the curve does not depend on alpha. And here you have to follow the pointer, please. As you know, to get the expectation value, we have to integrate this. So basically, we have to consider all the surface area under each curve. And sometimes we get more surface from the red curve, for example, right here, and less in the green. But then it's compensated by the surface area here. So in fact, the point is that even though the curves are different, the integral are the same. It's the reason why the average energy, kinetic or otherwise, is a constant and only depends on the temperature. So basically, we can write this like this. If the energy is alpha x squared, then the expectation value of the energy will be 1/2 kBt. That's an extremely profound result. This is an extremely, extremely profound result. And we will see its range of applicability in a few minutes. But before we do that, let's imagine that we have an energy that's not just one term, alpha x squared, but a sum of those terms. We already saw an example for the one-dimensional harmonic oscillator where we had mv squared over 2 plus kx squared over 2. So that was two terms. So let's suppose that you have a number n of terms. So if we want to calculate the expectation value of the energy of this, of course we find, or the mean energy or the average energy, these are all synonymous, we find that we have to calculate the energy times the probability, and we have to integrate this. Okay, we have n different variables, n being, for example, 2 for the one-dimensional harmonic oscillator. And then we calculate this integral. We replace the probability by the Boltzmann distribution. We find this, and then again we find that we have terms that just look the same as what we've seen before. In fact, the sum can come out of the integral, which means that we have to calculate right here the same terms as we had before. In other words, what we find is that the expectation value of the energy is now a sum over all those variables from 1 to n of 1/2 kBt. So this is actually crucial because it makes sense, of course, because we know that the expectation value of energy did not depend on alpha. So of course we don't find any alpha there. But the expectation value of the energy, of the total energy, I would say, the expectation value of the total energy will be given by a sum of 1/2 kBt for each degrees of freedom, if you will. So that's very deep because the expectation value of the energy will only depend on the temperature and the number of degrees of freedom that you have in your system. And we are going to see a number of examples here. So of course we get the expectation value is n over 2 kBt. Very good. Let's try to keep going. So each quadratic term is a mode or a degree of freedom of the system. So this is a definition here. So I just told you degree of freedom. Some author call it a mode. So we have n is the number of mode. For example, if you go back to our example of our one-dimensional harmonic oscillator, it has 2 modes. I mean, that's important. And so that means that each mode of the system contributes an amount of energy 1/2 kBt. This is the equipartition theorem. That means that each mode has an equal amount of energy associated with it. And we actually get to a more clear description of the equipartition theorem based on what we've just done, that if the energy of a classical system is the sum of n quadratic modes, and if that system is in contact with a heat reservoir at temperature T, then the mean energy of the system is given by n times 1/2 kBt. We will see the range of applicability of this equipartition theorem in just a minute. So, but the energy is equally distributed among all degrees of freedom, hence the equipartition theorem. Let's keep going. Let's try to think a little bit more. First of all, there are 2 important things on this slide. The first one is that when we talk about kBt or 1/2 kBt, that number does not depend on the mass, the size, or the composition. So if you take 2 gases that have different composition, that have different mass, if they have the same number of modes, they will have the exact same thermal energy stored in them. This could look a little surprising, but it's important because that means now that if you take, for example, a gigantic system, I'm talking about macroscopic system, if we can describe it with 1 mode, it will actually has as much energy, actually the exact same amount of energy, and if you take a single atom, if that single atom can be described by also 1 mode. So of course, it's the same amount of energy, but applied to a completely different system. Therefore, the thermal energy might have a negligible effect on the macroscopic object, but will have a huge effect on the small object. How do I know that? Well, because if the thermal energy is kBt and it is distributed in mv squared over 2, if m is small, then the velocity is going to be large, okay? And the other way is true too. We'll go in a few more seconds. One thing that students should always do is to try to have at least an idea of what kBt is at room temperature. So I listed a few terms here. So one thing the physicists should definitely know is that at room temperature, it's 1/40th of EV or of 25 millieV. They should, if they are spectroscopists, they should know kBt is about 200 wave number. And if they are doing chemistry, they should know that it's 2.41 kilojoule per mole or 0.58 kilocalorie per mole. It's a very good idea to have those numbers in mind to know if those numbers have if the thermal energy kBT has an impact or not on the physics that you're trying to describe. Let's try to see a few examples now. The first example I like to discuss is a pure translation of a monoatomic gas. We're going to say monoatomic, so we don't have to worry about additional degrees of freedom. But if it's if there is a simple translation without any potential in 3 dimensions, of course, that means that the energy is just the sum of the kinetic energy along the 3 axes, x, y, and z. So the number of modes is 3. Therefore, the average kinetic energy will be 3½ kBT. Okay, and I'd like to attract your attention about this 3½ kBT. It shouldn't come to a surprise to you if you have reviewed previous lectures. In fact, if you go to lecture 5, so that was a long time ago, we actually, and this is where we go on page 76 in lecture 5, we found 3½ kBT using the kinetic theory of gas. So let's keep going here. Okay, let's keep moving here. Very good. So let's try to have another example, and let's look at the rotational motion of diatomic gas. So we're going to suppose that this gas does not vibrate. So it's a rigid rod we have there. So there's no vibration yet. We'll do that. Don't worry. And then there is a term of rotation, and it's shown by the angular momentum L1 in this direction, and there is another one in this direction. So we are neglecting the rotation in the other direction, since it does not change the system at all and doesn't store energy. So basically, we have 2 terms that are 2 kinetic energy terms that are L1 square over 2II, which is the moment of inertia right there, along one direction and the other. So this is an azeotropic system, so they're probably different. Actually, they are not probably different in this particular case, but in general, they can be different. And then we find, of course, that the total energy of this system is motions, translation, the 3 translation, then plus 2 rotation. And of course, you can already guess the amount of kinetic energy this system can store. And of course, you know it's 5½ kBT. 1½ kBT per mode per degree of freedom. We have 5 of them, and that's it. This seems to be like a formidable task to do. If somebody came up to you with this kind of energy and said how much thermal energy is stored in there, that would be a big deal to calculate it. But it turns out that with the equipartition energy, this is pretty simple. It's 5½ kBT. Now let's try to add one more term, actually 2 more terms. So we have these 5 terms that we've already seen, translation, rotation, and suppose now that they can vibrate. Okay, the 2 motion 2 system can vibrate. So there is an energy that comes from the spring being compressed and elongated. This is a quadratic term. And of course, there is a kinetic energy of this system moving around the reduced mass mu, which is the reduced mass of this system here. So of course, we have 1, 2, 3, 4, 5, 6, 7 degrees of freedom. And of course, the kinetic energy that's stored in that system will be 7½ kBT. That's nice. Now, it's interesting now to remember what is the heat capacity. So how much heat can be stored in a system like this? Well, you remember the heat capacity is the amount of energy you need to raise the system by 1 degree. So in other words, the heat capacity is the change in energy with respect to T. And if you go back to the equations that we've seen, especially in terms of the Maxwell relations and so on and so forth, we find that the heat capacity was the first derivative of the energy with respect to temperature. And this is what we found. And of course, since if we have this in general, we find that the change in energy with respect to temperature will be F2 kb times F2 kb. But of course, if we want to have this number per mole, we replace kb from its expression from the number of Avogadro and the constant of gas R, and we find that per mole, the heat capacity at constant volume will be Fr over 2. So this is what we find. And in fact, we can also calculate the adiabatic index, which is Cp over Cv. And in that case, we find that the Cp is 1R above Cv, and we get 1 plus 2 over F. F being the number of degrees of freedom that the system can store kinetic energy in. So that makes a lot of sense, and we all understand this very well. Very nice. So let's keep moving. Yeah. So this is what we use as Cp. So this is basically what we have. The hardest part is to, I mean, which is not hard really, but the hardest part is to find F, which is the number of modes for the different systems. So this is a summary of what we've seen before. So let's try to look at the heat capacity of a solid. So imagine that you have a cubic solid. This is not always the case, but imagine this is the case, and we have each atom that's connected to 6 neighbors. Okay, just imagine the spring here, and we are going to do a very simple description of the solid as being attached by spring, harmonic spring. In reality, this is okay. This is an okay description, but it's not a very accurate. Of course, models that are used these days are much more accurate than this, but this gives you a good idea of what's happening. Okay, so there's no translation because it's a solid. So a solid is treated as being infinite. So there is no translation. That makes sense. There are 6 neighbors. So let's try to count this right. So how many springs do you have? Well, we have 6 springs per atom, so that's 6n. But remember, each spring is shared by 2 atoms. So if I have n atoms, I have 3n unique springs, right? So if we have a spring, we have 2 terms. We have the kx squared over 2, if you will, and we also have the energy, the kinetic energy of the movement. So we have 2 modes per spring. So that means that the total number of modes is 6n. So we have 6n modes. Therefore, we find that the energy on average that's stored, the thermal energy that's stored in a solid is going to be equal to 3n kBt. Nothing really surprising. I mean, this is always the same phenomena, same approach we use to getting this. And of course, we can calculate the heat capacity, and we find that the heat capacity is 3n kb, just the same way as we did before. I made a derivative of this term here, which means that per mole, Cv is equal to 3R. Okay, so n kb is equal, if n is the number of Avogadro, n kb is equal to R, as usual. And so this is interesting because that means that the heat capacity at constant volume is a constant 3R. And this is known as the Dulong-Petit equation. This is, I think it was one of the original figure here. And it shows that here this number 6 actually means, it exactly means Cv equal 3R. And so you see that when the temperature is high enough, many solid like lead and aluminum especially, they get to 3R. I mean, some systems don't go to 3R so fast, but this theory here that we could describe just in maybe 20 minutes is enough to explain the limiting case at high temperature. We know something is going pretty bad at low temperature. So this is something that we are going to study later in this lecture. But the point remains that at high enough temperature, this theory works pretty well. And this is the Dulong-Petit equation. Yes. So it's time now to look at the limitations of this equipartition theorem. So whenever you do a theory, you should never ever forget the constraint and the assumption you made, because forgetting assumptions and constraints that you impose at the beginning is a recipe for disaster. That means that you are tempted to apply your findings into a range of parameters that they were not designed to be included in the theory. So let's try to see which one they are. Of course, in this case, I were a little bit hidden, but I hope I'm going to make them clear to you. First of all, when we calculated the expectation value of the energy, we actually calculated this integral with the Boltzmann factor. Seems pretty innocuous, right? Well, the problem with this equation is that that means that we implicitly impose x to be a continuous variable going to minus infinity to plus infinity. So you've seen in your quantum physics courses, and you will probably see this more in more advanced quantum mechanics courses, that usually the variable that matter are quantized. They cannot take any values. So if they can't take any values, using an integral is certainly an approximation. And we are going to study a little bit when this approximation is acceptable or not. So this is already a big deal. So this equipartition theorem really is not compatible with quantum mechanics. It can still work under some conditions which I'm going to describe in a second. In fact, it's only and this is the main important point that sometimes students have a hard time to get, but the equipartition theorem still works at high temperature. And the reason why they work at high temperature is because in that case, the kBT, so the amount of thermal energy, or half kBT, if that value is larger than the difference between the energies from quantum mechanics, then the integral is a good approximation. Let me try to provide you a little bit more insight into this. So what I've done here, believe it or not, on the left-hand side, this is not a block. This is actually a series of many levels that I put together. Okay. Of course, you don't see because the resolution of your eye or even the screen is actually lower than the distance between the lines. But believe me, there are lines in there. There are lines in there. And suppose that we work at high temperature, and the high temperature is such that it's represented by the range I've plotted there. And of course, that at that level, the integral is a very good approximation. It's fine. So let's try to zoom a little bit, and let's represent the small parentheses on the left to the right parentheses on the right. And this is what we get. So we start to see the levels here. And so we say, okay, fine, the integral is good. But let's suppose now that I take a medium, a little bit lower temperature like this. And then you can tell, well, the temperature is such that kBT still significantly larger the distance between the levels. So probably the integral should still be a pretty good approximation. And it is, in general, it is. It's not perfect. It starts to show some problem, but it's okay. So let's try to zoom a little bit more. Okay. So if I zoom more, I end up with this, and of course there are more layers on the left and on the right. This is schematic. If I do this, I get a zoom, and if I use a very cold temperature, which is about the size of the distance between the levels, I find that in that case, doing the integral is a wrong approximation. So at low temperature, the equipartition theorem starts to break down, and in fact, we saw it in the CV versus temperature in the Dulong-Petit equation, that we would only the heat capacity would only approach the equipartition limit at high enough temperature, and this is the reason is exactly for this reason. Okay, so this is important to understand this. So if it was not clear to you, pause this screencast and try to think a little bit about this yourself. Why the integral is only a good approximation on the left-hand side and a pretty bad approximation on the right-hand side, and an okay approximation in the middle. So this is the usual limitation that we have in equipartition theorem. It's a low temperature. There is actually also a limitation at high temperature, which I should mention to you, which is for a different reason, and I'm going to explain that to you, and I think it's going to be pretty clear. If you remember, we did this. We actually use a Taylor series to approximate the potential around the zero, and then we found something like this, right? That we can use a harmonic approximation, and it works because so long as we are at low enough temperature, the movement of the object in that potential is going to be limited to the harmonic part, to the parabolic part. Okay, So let's try to do it again. So it doesn't go very far away from there. So that works really well. That works really well. Now suppose for a second that we are at a much higher temperature. So you see, at much higher temperature, the object can go much farther away and start to explore the actual potential, right? This is the full curve, which is deviating more and more from the harmonic approximation. Okay. So in that case, what's happening is that we have an harmonicity. It means that the potential can no longer be approximated by a quadratic term, and then everything we said so far, that the term, the energy term, were all quadratic, of course, is falling apart too. So there may be there is a lot of research right now in the on harmonicity and the fact that the systems are not quadratic, and in fact it leads to nonlinear physics, and nonlinear physics is actually pretty fascinating. So that's something that can happen at high temperature in some system, and this is important to notice. So before I end this lecture, I'd like to talk a little bit about Brownian motion. There's a lot of text on this slide, so let's not worry about it. But the point is that we are going to review this Brownian motion in detail in a later lecture. But the Brownian motion that was discovered in around the early 19th century by Robert Brown was actually the effect is to see that if you look at little piece of pollen, for example, in air, you see they are jiggling about. It has nothing to do with the gravitational pull or anything like this. It's actually to the fact that they're just moving around, seems to vibrate in a random fashion. And there were a number of people who looked into that to understand it. The first one was Christian Wiener in 1863, and of course, famously Albert Einstein in 1905. One of the reasons why he got the Nobel Prize later was to explain, in fact, that this kBt over 2, so the presence of some energy, that's thermal energy per degree of freedom, exists for all particles, regardless of their mass or size. So just like I mentioned maybe 10 minutes ago, if you have a small, tiny object like a pollen, like a piece of pollen, for example, that's a very low mass. It's the kBt over 2 is still going to be present in every single mode of that describe the motion of that pollen. And so if the mass is very small, that means that the kinetic energy mv squared over 2, I mean, the kinetic energy mv squared over 2 is going to be kBt over 2, right, on average. If the mass is very small, that means the velocity is large enough that you can actually see it with pretty modest microscope. So that's basically the fundamental reason why the Brownian motion exists, and we will come back into that later in this course. So it's time to go to the summary of this lecture. I hope that that I could convince you about the equipartition theorem, explain to you the where it's coming from, but also to make you remember that there are some issues with it. There are some issues, especially at very low temperature and also at very high temperature. So very low temperature is because we start to see the granularity of the energy level, basically in the quantization due to quantum mechanics. And at high temperature because we lose the harmonicity, which means that the assumption that we can write the energy as a sum of quadratic terms is no longer correct. So both conditions, of course, are usually pretty far from the application of this in practice, unless you are really looking into quantum mechanical effect. But the prediction of the equipartition theorem, especially on the heat capacity of solid and the heat capacity of gas, have been pretty important. And we of course know that some of those results are not correct, as you know, because the heat capacity, for example, if you remember the previous lecture, the third law of thermodynamics clearly indicates, so that the entropy is zero at zero Kelvin, indicates that the heat capacity has to be zero due to the third law of thermodynamics. If you forgot, please go back to the previous lecture. Here, what we find is that the heat capacity is constant, right? It's for example, it's 3R for a solid for any temperature, does not depend on temperature, which clearly shows that at low temperature, the whole thing breaks down, which is, of course, what we demonstrated at low temperature, where the quantum mechanical effect and also just the fact that we have to consider the interaction between the particles start to play a big role. So thank you very much, and I'll see you on next lecture, lecture 20, which will be on the partition function. Thank you.